Good day, my name is John Arnante and I will be discussing inner product spaces and orthogonality. So an inner product is a function that takes two vectors as an input and returns a scalar, which is also called a dot product. Properties of inner product. The first one is commutative property. This property is expressed as u multiplied by v equals to v multiplied by u. The second is distributive property. This property is expressed as u plus v multiplied by w and equals to u multiplied by w plus v multiplied by w. The third one is scalar multiple. This property is expressed as c multiplied by uv equals to cu multiplied by v and equals to u multiplied by cv. And the last but not the least property is non-negative property. This property is expressed as u multiplied by u greater or equals to 0 and equals to 0 greater or less than u is equals to 0. So example number 1 for dot product. Let u equals to -3, -1, and -5 and v equals to +2, -4 and -2. So it will be u times v. It will be -3 times 2 is equals to -6 plus -1 times -4 equals to +4 plus -5 times -2 equals to 10. So -6 plus 4 plus 10 is equals to 8. Example number 2 for distributive property. So for this property, it is expressed as u plus v multiplied by w and equal to u multiplied by w plus v multiplied by w. So u is 3, -2, and -5, and v is -1, 2, and 1, and w is -2, and 3, and -3. So both sides are equal to 8. For orthogonality, two vectors are orthogonal if they are perpendicular to each other, performing a 90-degree angle. This is determined by their dot product being 0. So basically, two vectors are orthogonal if their product or dot product is equal to 0. It means that they are perpendicular or in 90-degree angle.
Here's an example to illustrate orthogonality. Take vector A, 3, 0, -4, and vector C, 4, 2, and 3. If we calculate their dot product, 3 times 4 plus 0 times 2 plus -2 times 3, that gives us 12 plus 0 minus 12, which equals to 0. Since the dot product is 0, these two vectors are orthogonal, meaning they are perpendicular. Now let's move on to the Gram-Schmidt process. This is a method that allows us to take any set of vectors and turn them into an orthogonal basis. The key idea is that each step we make a new vector, orthogonal to all the ones before it, by subtracting it out its projections. By the end, we'll have a whole new set of orthogonal vectors to work with. Here's how it works in the first few steps. First, we set v1 equals to x1. Next, we create v1 by subtracting the projection of x2 onto v1. Then, for v3, we subtract both the projection onto v1 and the projection onto v2. Each time, we're removing the parts of the vectors that overlap with the earlier ones. So what's left is orthogonal. In general, the formula looks like this. Vk equals xk minus the sum of projections of xk onto all the earlier vectors. So instead of writing each step individually, this formula summarizes the entire process. It tells us that every new vectors is constructed by taking xk and subtracting its overlap with all previous vectors. Let's apply the Gram-Schmidt process to an example. Suppose we start v1, 1, 1, 0, v2 equal to 1, 1, and 1, and v3 equal to 3, 1, and 1. After going through the steps, we end up with an orthogonal basis 1, 1, 0, 0, 0, 1, and 1, negative 1, 0. Notice that each step of these final vectors is perpendicular to the others, which is exactly what the Gram-Schmidt process is meant to achieve. To sum it all up, the dot product lets us check orthogonality. Orthogonal vectors have a dot product of 0, and the Gram-Schmidt process is a systematic way to take any set of vectors and turn them into an orthogonal basis. These concepts are essential tools in linear algebra and have a wide application in geometry, computer science, and beyond.